Hello everyone. So in the last lectures we have discussed about plastic wave, and before that we discussed about elastic waves. So now we will move to another chapter, that is shock waves, which is we discussed earlier in, this is a part of the plastic waves only, but we will start with the little introduction of shock waves, probably not very specific to the impact problem of shock waves, but the general shock waves we will discuss first. So examples of shock waves, I mean what you probably heard of is explosion, and then bullets moving, bullets or projectile moving at supersonic speed, or similarly aircraft traveling at supersonic speed. So when you talk about this bullet or aircraft moving at a supersonic speed, suppose this is the bullet or aircraft we are drawing, so we can see the shock waves actually. For especially for aircraft we can see the shock wave, but for bullet probably it not possible through the naked eye. But this is the envelope produced by, let's say, aircraft. This is the aircraft, and we can see a envelope, see shock wave, envelope. So similarly you can you will get such envelope of a bullet traveling at a very high speed. So these phenomena, so whatever it is, explosion or high speed bullet or high speed aircraft, so these phenomena create a very large changes of pressure. I'll write P for only pressure, and pressure, temperature, density at very short duration of time. So basically we will more focus on first pressure, but even for temperature and density will also have a very abrupt change at the shock wave front. So this shock wave we can compare with sound wave. So there when we call it a sound wave, they are actually small amplitude wave, compression actually wave, they are compression wave. And in case of shock wave it is a finite amplitude wave. So it is very similar to the sound wave, but it is a finite amplitude. That means it has a big amplitude, bigger than the sound wave. And sound wave, the speed is, we call that a sound speed, but here in the case of shock wave, so it travels at a higher speed than sound speed, higher speed than local sound speed at a local temperature. So local means locally whatever the temperature, that will decide the sound speed, and in case of shock wave it has a higher speed than that. So that is one characteristic. And generally after propagation of the wave, after propagation of sound wave, the state of the medium is unchanged. Medium is unchanged, and in the case of shock wave, the material or the gas or other, let's say some solid material, will be generally at higher temperature or pressure after the passage of shock wave. So that way actually it is irreversible. Some changes happens during the passage of shock waves. So for sound wave, the medium will be the state of the medium will be unchanged. So the persons behind these, the researchers behind these shock waves research in the very early years, 100 years ago, even more than 100 years ago, are Stokes, and then Earnshaw, Raymond, Rankine, Huguenot, and Rayleigh, Lord Rayleigh. So these are the researchers. They are the researchers who were the pioneers, who did the pioneering work on shock wave. Shock fronts on gas. Most of the researchers, they worked on shock waves they produced in the gas, and they used equation of ideal gas dynamics. So they have used the ideal gas dynamics for their findings, for their calculations. So in that time they have used the conservation of mass, momentum and energy in an ideal fluid, and also this in this calculations, heat conduction and viscous stresses were ignored. So viscous stresses, these are ignored. That means all the thermodynamic changes are adiabatic and reversible. So all the thermodynamic changes are adiabatic and reversible. So these are what we discussed is the works of the earlier researchers. So they worked that way, and so what will happen when the amplitude of the compression wave is finite? So for the sound wave, and the amplitude is small amplitude, and the sound speed is related to pressure, like partial of P with respect to rho at constant entropy. We can this is the local sound speed, C is the local sound speed. So we have a relation like this, but for shock also this has a finite amplitude. The pressure change, let's say change of pressure is of the order of the pressure P. So that's why we call it a finite amplitude. It's the amplitude is very high, so delta P, the change in pressure is of the order of the pressure P. So the variation of pressure, it implies that the variation of sound speed as well. This is, we'll write C for sound speed. Each point on the wave form, we will write wave form, that is not the front, that the configuration of wave is the we write it as a waveform, propagates with a local sound speed. So that means at different points of the wave may travel with different sound speed, local sound speed. So how this pressure is changing with distance, so how this we call the steepening happens. So this is, let's say in the y-axis, this is pressure, that is, we'll write gas pressure. So this was by the way, I just forgot to mention about my reference. This is not directly from our textbooks or the reference books. This is most part of the discussions are a document on shock waves versus sound waves from Los Alamos. This is a report, this article published in Los Alamos, Science, from where actually I got most of the references. So you can have a look at it. That's a very brief report on shock waves from Los Alamos lab in of USA. So what we are going to plot is, with x minus ct. We got this earlier even for our elastic wave calculations, the wave equation, general solution of the wave equation. We have a function or one variable we are taking as x minus ct. In this case also, if you think that x minus ct gives a constant value, so let's say x minus ct equal to 0. So what will happen is so x will be equal to ct. That means with increase in time, if time is increasing, so x will increase. So that's why it's in a positive direction. This waveform will move in a positive direction. So what we are seeing is here a waveform, and that is at, let's say, at time equal to t1. So this is the change in pressure delta P, and let's say this pressure is changing. and so this is, let's say, at 0 level. So now what will happen is, at a time t2, as we already discussed, that the each point on the waveform will travel at a different speed. So what it will do is, it will generate something like this, because at the top point will move faster and the bottom point will move slower. So c minus c plus delta c, and this is c minus delta c if the, let's say, the point in the middle. So, or otherwise I can just remove the middle line. So in the point in the middle, it will move at, let's say, c. So why it is happening? We already discussed earlier that the delta p, the variation of p will change the variation of, will imply this variation of the c. So changes in pressure will lead to changes in the speed. At higher pressure it has a higher velocity, and at a lower pressure it has a lower velocity. So in this way, if it continues, so what will happen is, at time t3, so at time t3, so this wave will look something like this. See, what will happen here is, because why it is taking this shape, because at the top point is moving at a higher speed and the bottom point is moving at a lower speed. So it will look like this at time t3. So and as you know, in the x-axis we have x minus ct. So then in this case, we will get the variables, state variables, will have a multiple values. So suppose state variables means, in this case it has pressure, state variables, pressure, maybe density, maybe temperature. So in this case, this is state variable pressure. So what will happen is, let's say this point and the same same position, it will take multiple values. So that's why it is, this actually is not correct. If you think that this predictions, the prediction means what we are doing is, on the basis of that pressure, the variation of pressure will vary the velocity. But in this case we got to know that if you do it, if you predict it like that, so what will happen is, the state variables will have multiple values, like multi-value function, multiple values at one position. So that's why what will happen is, it actually in reality is, it will form a front, straight front. That is called shock front. So what are our predictions? Our predictions was that from the pressure velocity wave velocity relations, or pressure sound speed relations, we predicted that the shape will be like this, this shape. But that cannot happen, because it's a multi-value, at the same position it will take multiple values of pressure or temperature or density. So that's why in reality it will take a sharp front. So it will something like this. In reality this will take a let's say vertical straight line. So this will look like this. So that is, let's say, at time t equal to t4, so we have this shock front. So this is p here, x minus ct here. So this is, so that's why we call this a steep wave front, or we call steep shock front. Okay. So now because of this is now single valued. So this is, you can see that this will be now in this case it will be single valued function. It has only one pressure value, single valued. So if you see at the microscopic scale, microscopic level, if you see that the large gradient in temperature, pressure, large gradients in temperature, and let us say velocity at the front of the wave, that the steepening wave that cause the irreversible processes. Irreversible processes, there is heat conduction, and viscous stress. These irreversible processes, what they will do is will dominate. These irreversible process will dominate at a in a very narrow region. So dominate in a very narrow region, and this will lead to the single valued shock front. So because of this, because how it is happening, these single valued shock front, if you see here, so because at a very narrow region, that means at the shock front, narrow region means it is at the shock front, so there are some irreversible processes like heat conduction and viscous stress happens, and that way the single valued shock front I mean it prevails. And in the macroscopic level, what happen is, this is what we talked about earlier, the microscopic. Now in the macroscopic level, the net effect is is conservation of mass, moment and mass, momentum and energy across the shock front. However, in this the entropy is not conserved. Entropy is not conserved. The entropy actually increases. The entropy increases because it is related to the kinetic energy, relative kinetic energy is dissipated into heat through atomic or molecular collisions. So that's why entropy increases. So we want to see in a pressure versus volume in a plot. So what we will see how these reversible or irreversible changes happen for sound waves and shock waves. So this is, if you have pressure on the y axis, this is gas pressure. So whatever we are talking about, these are for gas, and then what we will be discussing will be on impact problem is solid material, but these concept of the shock wave will remain the same. Mostly it will remain the same. So what we will we can have is we have let us say at a point at a state 1. So at a point 1, so if you draw the isentrope, so one entropy line, let us say it's isentropic line, this is SA, and the another one, so what we will, SA, and then what will, this is the first position of the shock wave. So when we made the shock wave in the earlier slide, so what is happening here is you have a shock wave front. The shock wave front is something like this, right? So when you x minus ct and then p, okay, so what is here happening here, whatever we are drawing is number 1 is the state just ahead of the shock front, let's say, and for the just behind the shock front, so just behind the shock front, suppose we have a state 2, so for that from 1 to 2 we need to draw a shock huguenot, and then this is our state 2, and then from state 2 what we will have an adiabatic adiabate line, and then we can find the state 3, which is the behind the shock front. This 2 is just across the this shock front, so but 3 is behind the shock front. So this will follow a adiabate, and actually this is an isentropic. So let's say this is our SB. Now the shock front is non-adiabatic. So when if you see that the front, that means from 1 to 2, this is non-adiabatic process. So this one is I would write here non-adiabatic. And if you see this, the state variables, like let's say P2 is higher than P1, or you can write rho 2 is higher than rho 1. Entropy, you can see here entropy is higher than S2 is higher, higher. So probably this, in this case this is S1 and here S2. So in these entropies, so this process, the passage of shock wave, after the passage of shock wave, this is the, this adiabate is, we can write that this is the result of passage of shock wave. And if it is in case of a sound wave, if it is a sound wave, so what will happen, it will remain the same. So if the sound wave, passage of sound wave, pressures of sound wave, that is not irreversible. So in this case this is irreversible. So why it is calling this irreversible? Because the shock wave starts from 1 and then it across the shock wave front, it will be the state is 2. So that means it's not a isentropic, the entropy is not the same. But in case of the sound wave, although there will be some pressure and then the medium will be compressed, and then it will, by the way it is a reversible process, it will come back to the same position. So the after passage of the shock wave, the pressure or temperature will not be high, but for passage of shock wave it will be irreversible. And so if you see what happens, our initial state of the state is 1 and our final is 3. So if you see here, initial state, initial state is 1 and then final state is 3. So in this case you can see that your entropy is higher, S3 is higher than S1. So in this case S2 and S3 are same. So S3 is higher than S1 here. We showed you, and even the temperature will be higher, and but pressure is actually probably this pressure will be same. That I haven't mentioned that actually the pressure will be same, the same pressure. The P1 is equal to P3. It will have a lower density, so the density rho 3 will be lower than rho 1. So basically the what we can see that the pressure will remain same after the passage of the shock wave, but the other variables like entropy and temperature and density, it will be changed, and that's why it is irreversible process. Any sudden release of energy in very short duration like in the order of microseconds can produce shock waves, can produce shock wave. Dissipation of energy, the shock wave is dissipation of energy happens during shock wave. So it can be energy can be mechanical or let us say nuclear. As you know, nuclear energy is very much used to actually to produce shock, or it can be chemical, and even it can be electrical. So dissipation of energy of any kind, and but in a limited space, can lead to shock waves. And then as I said, the dissipation of energy is the shock wave. So that's why the dissipation will require a medium for dissipation of energy. So that's why shock wave does not form, is not generated or propagated in vacuum.